Well, good morning, everyone. My name is Mike Booth. I'm with Intergank Ventures. I want to thank you all so much for taking the time out of your day to join us for this webinar. I think we've got a really great webinar for you all this morning. I would like to introduce Dr. Sergey Lincoln from Texas Scientific Products. He's going to do the first part of the webinar for you all today, focusing on, this how to essentially tips for running really challenging ICP applications. So some really good information there. But before I turn it over to Sergey, I do want to mention if you have any questions, please submit them. We love answering questions. So if you use the Q&A button that you should see at the bottom of your screen, that way we can keep track of the questions. We know which ones we've answered. And then, if we for some reason run out of time, that also allows us to keep those questions and respond back and give a written response to those. So we'll answer questions at the very end. But please, as you have questions, please submit them through the Q&A box, and Sergey and I will be happy to answer them at the end of the presentation today. So without further ado, Sergey, I'll turn it over to you. And thank you all so much for joining us this morning.
Okay, Mike, thank you. Thank you for the introduction. And yeah, thank you folks for joining us. We know you're busy, and we'll try use your time appropriately so you can hopefully learn something from spending some time with us today. So today's session is we continue our educational series that we do in partnership with Organic Ventures. And today we focused on, or we're going to focus on how to run some difficult stuff. Because easy stuff doesn't present a challenge, right? But what if you run to something that really present a difficulty and you're running into some problems? So what is we'll try to find like a practical way to address that. When I was thinking about putting this presentation together, so I was thinking where to start from, right? Because usually it's better to start from simple and then go in a step up and increase the complexity with different things. And usually, like organic application on running oils not come first. But when I looked over what the information that I've got, it turns out that running oils was probably the simplest from this list of tough applications that we're going to be talking about. So let's dive into it. Why the first challenging application are oils. There are different type of oils. If you are running like lubricating oils, or maybe some wear metals in used oils, it could be challenging. But the most challenging are some of these that you can see on the picture that was shared by some of our customers. So crude oils, you look at that and you don't just see the consistency, which is pretty rough, right? It's a color, but there are also some particulate and things like that. The There are other type of oils, and that's also in petrochem that are even solidified at room temperature. And what you see here is this vial that turned upside down and nothing coming out of it, right? So the other example of this type of oil solidified at room temperature would be waste cooking oil from food chains. So that used in the biodiesel productions and things like that. So how to run this? Typically, when people go from running aqueous to organics, so then the change of setup is relatively straightforward. So you need to have certain some production components, and for the most part, they are similar. You just need to have a dedicated set of glassware. You can use the current one that you have for aqueous, but then you're going to be cleaning if you go in between. So it's better to have a dedicated set. So one of the things that definitely specific about running oils, you need a double pass spray chamber, not a single pass that you may use for your aqueous samples. And it could be either cyclonic, like shown in the picture here, or if you have a Scott. The other special about running oils or any organics is you need to use a narrow injector, torch injector ID, because uh, when samples are diluted in solvent, even in the like a basic solvent, not like very volatile like xylene or toluene. So then even with kerosene type of solvents, there is more sample going to the plasma, and you need to slow it down. That's why typically a smaller or narrow injectors ID are used. And of course, you need to use the pump tubing that's going to withstand the solvent. So the also one of the key components in successfully running oil analysis is robust nebulizer. And because if I when I see on the picture of the samples here something with particulate and uh, pretty heavy consistency, you definitely need something that can handle it. And actually, ASTM method for running oil specifically calls for a Babington type nebulizer that's also can handle particulates and things like that. So we're not going to dig into the specifics of the or details of the nebulizer selection. I will refer you to our previous webinar that we ran actually with Mike a year ago, and that's specifically dedicated to different nebulizer designs and dives into it. So please, you can look at this at Inorganic Ventures YouTube channel or website, or at our YouTube channel. So when you get this set up and then you start to run organics, so what happens next? You will see here, the plasma is alive and everything looks good. And then when you started to look a bit more closer on your torch and your injector, you see a carbon buildup right there. So what happens? And so this is typically what users experience when they switching from aqueous to organics and without adjusting any parameters. So, in order to address that, it's a very simple solution. So, what you need to do is to increase the auxiliary flow, or it's called intermediate flow, on some of the instruments, and that will lift the bottom of the plasma up, like shown by this arrow, and that will prevent the carbon buildup that you can run consistently for hours and hours and hours before you need any cleaning. So this is probably one of the most critical thing in running organic applications. So here is an example of the plasma parameters on one of the instruments. And you may need a higher power setting. Well, you definitely need a higher power settings, a bit of a higher coolant flow as compared to aqueous. But again, what's more important is the most important is increase the auxiliary flow. So here it's 1.5 liters per minute. And I don't know, probably the regular settings for aqueous probably would be zero point 0.7 to zero point 0.8. So the rule of thumb or the ballpark figure, if you're going from aqueous to organics, you're about to double your auxiliary flow so that you can run smoothly. So then we're moving from organics to aqueous samples, so kind of reverse. And here is a couple of examples of aqueous samples. So here is the one of the industrial waste that has a couple of percent of PCBs and diesel and you name it. And see there is a separation of aqueous and organic phase here. So that's pretty good looking stuff. The picture on the right represents what we call backflow waters or hydraulic fracturing waters that have extremely high TDS content that used in the oil production. In the same category fall all oil field brines for used for lithium extraction. So when you start to run something like that, and here is the live picture of the plasma. So the plasma turns to pretty, nice, nice colors, right? But in addition to these colors, so what's happening there? And here is the picture for comparison looks similar. This is a oil field brines used for lithium extraction, so it's also loaded with a lot of salts. So how to run this type of samples without relatively smoothly and reliably? So here is the setup and key components that you need to be aware of. So number one, your torch, or if you have a demountable torch, it's injector of your torch. If you remember on if you go back and mention to organics, right? We were talking about having a narrow injector. Here it's opposite way. We need to have a wider bore injector. The size of the injector depends on your instrument manufacturer. It's somewhere, for example, you have 1.8 millimeter for aqueous, it will go to 2.5 for high salt. So you got to look at what your ICP manufacturer offers. For example, on PerkinElmer instrument, there is a number of injectors going from, I believe, from 0.8 millimeters to 1.2, 1.6, and further. So the injector ID, it has to be wide. That's number one. So number two, usually I put a humidifier somewhere, after the nebulizer spray chamber and things like that. But I guess recently, within probably last year, so what we experienced by talking to our customers, so they may have a right nebulizer, right spray chamber, but the argon humidifier is missing. And the users people are struggling because it will salt up any nebulizer, whether it is high solids capable or not high solids capable. So in order to maintain a good health of your nebulizer, so the argon humidifier must be in line, which is basically a vessel with different designs. You can see one of those. So, but it will moisturize the nebulizer flow, and it will slow down dramatically the what we call salting up of the gas orifice of your nebulizer. And then, of course, you need to have a robust, high solids capable nebulizer, and again, double cyclonic spray chamber, not a single pass, because with a lot of salt and sample load going to the plasma, your plasma may not get sustained and it will shut down on you. So that's why you need a double pass spray chamber. So the other thing that we highly recommend, and you may get away without it for certain applications, which I will show you a bit later, but the setup with additional gas introduction is very beneficial when you run something like that. So here is one of the examples. So you have an adapter here, and then the additional gas is being introduced into this area here. It's sort of like ICP-MS folks, they are used to it because there is all the instruments are equipped with called makeup gas. But the functionality of it from additional gas here, or sometimes it's called sheath gas, versus what's going on here is very different. So what happens is, so you get your aerosol, and the aerosol travels here, and then the gas, additional gas, is introduced. It's argon, and then it surrounds the aerosol, and it travels like in the envelope, and there is a barrier. The additional gas build a barrier between your aerosol and the walls of the injector of your torch. So that creates the very good environment for aerosol, for high salt aerosol to travel through the torch without any depositions. Or these depositions are going to be slowing down dramatically. So the other thing, again, using analogy with organic samples, is, when you run something like that and it has a lot of salts, so you need to increase the auxiliary flow. Otherwise, the salt is going to be building up on your injector, similar what carbon builds up when you run organics. So again, increase your auxiliary flow. Again, rule of thumb, going from regular non-TDS samples to high salt, about factor of 2. So then the next thing on the list in our complex or tough applications is what's called diesel exhaust fluid, or abbreviation of DEF. So that's the chemical that used in diesel engines to reduce emissions. So the issue with it, why I put it at the top of the chain of difficult samples. You see the picture here. The DEF contains 32.5% of urea, and it crystallizes instantly. So here is the example of, you see these crystals here, and that's around the rinse station of the autosampler. So where it came from. So when your autosampler probe travels and goes from sample to rinse and goes back to the sample, on the way to the rinse station, it could be some drips, and these drips of the sample, or drops, accumulated here, and this is what you see here. So it crystallizes instantly, and you see that's also around this area. So imagine what could happen to, I mean, the similar thing happens when you're running through your torch and your nebulizer and all of that. So that is why, for this particular application, uh, engaging the additional gas, I think it is, I would say not a must, but definitely a very good thing to do. So you can run reliably. Here are different pictures from different instruments showing that your instrument might have already a setup for additional gas. So here is how it looks on Agilent. It's called makeup gas. This is from Thermo, and this is from Spectral. Now, what happens if your instrument doesn't come or doesn't have this hardware set up? Well, in this case, yeah, you can set up a mass flow controller to introduce this gas externally. So here is the example how it looks like, or how it might look like. That's what we did for one of our customers. So you can set up on the side of the instrument and then plumb the argon in. So obviously the mass flow controller have to be connected to a source of argon. And yeah, so here on the right you see a picture that's showing about how much of the additional gas is going on into the system. So when we look at some data, so what was the outcome? So recently the detection limits were became more stringent for these DEF fluids, and one of the critical elements is potassium. It's quite difficult to do, because you see the spectral environment around potassium because of the organics. But just by introducing or plumbing the additional gas, it allows to run urea just at 1 to 1 dilution, or 1 + 1, 1 to 2, which is 50% dilution. And before, people were able only to run it to 1 to 5, 1 to 4, 1 to 5, which will obviously affect the detection limits. So here you can see on this data that, yeah, the 0 and 10 ppb solution is blank is on the same level, but it clearly separates 50 ppb. So your detection limit here probably somewhere around probably 25 ppb or something like that, probably quantifiable like that. So that is the effect of getting additional gas on top of be able to run it reliably. Yeah, that's the point here. Okay. All right. Now, next application that I wanted to bring up to you is some clinical by ICP-MS. Why is that? So you see that there is a in clinical samples in blood or serum, the protein coagulation happens and cell precipitate, and they form this precipitate right here. And what's happening? It will cause the nebulizer clogging. We just published the article in the spectroscopy of September 2025 that has details on how it is run and what nebulizer was used for that to run successfully. But here, just a few highlights. So one of the interesting things that we did when we ran this thing was we ran the issue of matrix match standards. And typically people fully matrix match direct blood with getting the blood from blood banks. The problem with that for us at that time was the I think it was COVID time, and the blood was not readily available. That's number one. Number two, even if it's available, it's hard to find the blood that will be clean for certain elements. So what we did is we took the paper, and that has just the data for total analysis, like 72 elements. The researchers in Germany, like Peter Hyland and co-authors, did this great work. And we looked at the few elements that have the highest concentration. This is ppb. And then if you divide it by 1,000, you see, for example, sodium here from 1,500 something to 2,000 ppm, potassium 1,300. So then the dilution factor on the way we run the blood samples are 1 to 20. And this is how we come up with a few elements that we created sort of like a synthetic calibration standard. So let's say 2,000 divided by 20, that's 100. So we did a little bit lower to kind of be, in the middle, closer to the high end of the range. So that's how this sort of matrix match standards were created. And then we took a reference material that was available and then ran the analysis. So you can see here the calibration study, stability over 12 hours. So this is the accuracy with these type of calibration standards. And yeah, Michael, we're gonna be talking about more details on some of the strategy for the calibration matrix match standards. But here's just an example of what we did, and it worked pretty well even without complete matrix matching with blood. So here is how sample introduction components looked like. You see this is why it's tough. That's how sample reduction components are affected. You see the deposit, and so the cones looked okay, but you see the deposit here. But the nebulizer, our nebulizer called Optimist Ion, looked absolutely clean, and there was nothing to be done to maintain it. But again, the details are in this paper that we just published in spectroscopy. So next thing that I want to bring up to you is the what if you have high accuracy analysis, and high accuracy means less than 2% relative error. Typical examples are precious metals, it could be fertilizers or additives in oils. So here is the example. We look at the calibration curve coefficient, right? And it looks very decent. So 3 nines, almost 4 nines. But then let's say we have to hit the target of 33%, right? And if you look at 2% relative error, it's only plus minus 0.66. So that's the range right here, right? So that's the range that's according to specs you have to hit. But then we look at the residual error, which is very often being overlooked. It's called residual error or relative difference in percentage, whatever. And see right here, everything is around 1%. So if you have to be within 2% target, but if you're 1% off on your calibration, so guess what? You're going to start to run it, and either your QC going to be off just a little bit through the tiny drift of your instrument, or you're not going to be providing the high accuracy data. So how to address how the curve should look like? So this is one of the example like from potassium in fertilizers. But then if we look at the relative percent difference, see this is how this is what should be the target. So how to adjust it is there is a play with you can do the statistical weight plane, apply statistical models to tie up these numbers, and then you will be able to get your approach the relative accuracy at 2%. So the next application is when the detection limits are very low, but what if you don't have ICP-MS for that? So that's again, I will refer to the paper that we published in Spectroscopy of 2023, and the work was done by Autumn Phillips, R&D chemist at Inorganic Ventures, and it was a collaboration work. So folks from CEM help us with digestion. And let's quickly take a look on why I'm bringing this application, because it involves not just the sample intro, but also sample preparation and the calibration strategy with matrix matching. That's a very good example on if you look from the 30,000 feet view. So what was the approach? It's a combination of three components. So in order to get this done, because typically the analysis, we're talking about analysis of cannabis for big four, arsenic, cadmium, mercury, and lead. And typically it's done by ICP-MS, but can be done by ICP emission. And here was the approach. So the sample reduction that very high efficiency that doubles the sensitivity. The second component is modifying or tuning the digestion methodology for two things: increasing the completeness of digestion by bringing the temperature up, and minimizing the dilution factor. And then on top of it, so we have to come up with approach to close match calibration standards. And here is why. So this is the high efficiency sample reduction system that was used. And then the samples was digested at high temperature, 230, specifically to minimize the carbon, residual carbon that's still present in inorganic samples. Even tiny amount, like typically it's less than 1%, but then you will see how it affects spectrally certain elements. And then we used 1 gram of sample and bring it only to 15 milliliters instead of 0.5 to 50 or 1 to 100. So we cut the dilution factor to be able to get, you see here, there is a picture of showing only 15 milliliters, 1 gram to 15 mils. And here is what happens spectrally, right? So you started to run, and this is a critical element there is arsenic. So arsenic is um, not one of the best elements of detection limits in ICP emission. And on top of it, you have this quite complicated spectral background. So in just pure nitric, right? Everything looks flat and clean, and then the spike recovers 30 ppb. Then when you start to introduce carbon, which is what we mimicked by introducing carbon into the experiment to mimic what happens in the real sample, right? You have this bump right there, and this bump, here we go, reads 4 ppb, 4 to 5 ppb false positive arsenic. This is what happens, right? So that's the effect of residual carbon on arsenic line. And so how to counter that? So the carbon was introduced to the set of calibration standard in the form of potassium hydrogen phthalate, and that would kind of matrix match the sample, and that eliminated this high bias that would come from carbon interference. In addition, we added about a few hundred ppm of calcium because calcium present in any plant samples, so that also affected this elevation of the background. So that was coming from calcium. That helped as well. And as a summary, so first, yeah, selecting the sample intra is probably one of the most important things. So you gotta get the right nebulizer, high solids capable for all of these applications, high particulate capable as well, a right type of the spray chamber, torch injector ID that you also have to pay attention, depends on what is the application. If you go organics or high volatile, so the inject ID should be narrow. If you go high salt, it should be wider. And then, as I mentioned, additional or makeup gas introduction is very, very beneficial. If you have procedure or that involved sample prep, yeah, it has to be, it could be tuned, it can be optimized, and the sample prep, like in case of the oil samples, I forgot to mention that like these samples that are solidified at room temperature, so you have to heat them up. People are heating them up to loosen them up and then make a dilution with a solvent. So then, if you run high accuracy analysis, yeah, look at your calibration data. So if your residual error or relative error in percentage depends on the terminology used by your ICP manufacturer. So you have to play with this statistical weight to bring your residual or relative percent error it should be better than a 0.5% at least if you're looking for 2% relative accuracy. And then, of course, the closely matrix match calibration standards that I showed by a few examples. But this year, I think Michael will continue on that. Yeah, one thing that I did not mention, and it's worth mentioning in the end, is of course using the internal standardization. It's almost a must in all of these applications that I mentioned. So this, I would like to thank you for your attention. Questions, please, at the end. We're going to be very happy to answer it. And Mike, I'm going to be passing it to you.
Awesome. Well, great. Thanks, Sergey. Yeah, so I believe that
Okay, I
I
stopped
should,
sharing.
yep,
Sorry,
I
it
should be
took
able
me
to
a while.
share. Oh, no, you're good. I should be able to share my screen with you all now. And I have a very Brief presentation that I'll be going through, just talking a little bit more about selecting the right standard for your approach. So as we go through this, I just do want to add a little bit of reminder before we get started on this presentation. This one will be pretty brief. So if you have any questions, please use the Q&A box in the at the lower part of your screen there to submit any questions. I've seen we have a couple good questions coming in so far, so we love to see that. Please keep that up. All right, so why is selecting the right standard so critical? It's basically because it's really the foundation of your whole analysis, right? You have all of these things that impact, the accuracy of your results, and really a big part of that is the standards, but also standards, if you choose the right standards, it can have an impact on your sample preparation as well. So there are a few things that, a lot of people don't think about in terms of selecting the appropriate standard. Um, a few options that might be available that folks don't really think about in terms of what is the best standard for your specific application. But try to keep all of these steps in your workflow in mind as we talk through, what would be the right standard for your application. So you have, your stock standards usually is where you're starting out. Typically, folks are preparing those to make some sort of working standards. At the same time, you're getting in your samples, you have to prepare those. Then it goes through the ICP analysis. And then hopefully you're spending the majority of your time on the data review and then decision-making process based on that data review. So before you select an appropriate standard, you really have to step back and review your application. And these are application specific things. So what is your sample throughput? So are you a high throughput application or not? Typically, if you're a high throughput application, you spend a lot more time, managing samples, looking at results, that sort of thing. So you want to try to minimize time in places that you can. We'll talk about that in the next slide. What's the variety type of your sample? Are you getting in a wide variety of samples, or are you typically running the usual type of samples? They're all pretty similar. An example of this might be, if you're running a lot of drinking water samples, or maybe you're getting in sample types that are just, off the wall. We've talked to a lot of people that, they'll show up to work one morning and they'll have a mystery package on their desk and they have no idea what it is, and that's their samples that they're running for the day. And then lastly, you need to think about what's the expected concentration range with your method that you're wanting to analyze. So are you trying to measure near either instrument or method detection limits? Because that can be a little bit tricky to pull off, and you want to make sure you have the right standards for that approach. And when you think about these factors you have to review for your application, there are also factors that you should review in terms of just your laboratory as well, that go beyond the individual method. And that could be, the overall cleanliness of the lab. Sometimes if you're doing large dilution factors, there are contamination risks, and we'll talk again about that more in a second. You know, what's the overall experience of you or your analysts, and what's their comfortability level with, preparing standards? That's something to keep in mind. So there are other factors that go along with these different applications that are more on a global kind of lab-based level at the same time. So all those factors you want to keep in mind as you select an appropriate standard. So we will sit down with folks if they have a question about what standard is right for them. And in those conversations, I typically keep these three factors in mind. First off is, we talk a lot about contamination. It's one of our most popular topics that we review when we do like either our ICP conference or seminar appearances. Everyone loves to talk about contamination risk. So that is something to keep in mind. Like I mentioned before, if you're doing high dilution factors, even a very small trace amount of contamination can appear to be very large after you've applied your dilution factor. So that is something to keep in mind. Next thing to keep in mind is the time. So how much time do you have? This can depend heavily on your sample throughput, but also on the complexity of your samples. There are applications that we run in our lab where I could probably test and, pass judgment on 100 samples before I could do two of another type of sample that we do. So keep in mind, what is the factor of time in your method. And then lastly is accuracy. Everyone wants to be as accurate as possible. But there are different applications where accuracy is more of a bigger deal than others. So Sergey had talked about, the high accuracy applications, being within 2%. for things like precious metals. There are other applications where people just want to make sure that they're within, 10, 20%. And there are some applications where it's really more of a trend analysis. So if your application doesn't call for a high degree of accuracy, then that's something you keep in mind during your sample prep. And it's something you have to keep in mind also. It kind of balances with these other factors. If you don't have to be extremely accurate, you don't have to worry about as much about contamination for certain things. But it's all sort of a balancing act. All right. So first up, when it comes to selecting a standard, just put it out there. There are two main categories of standards that Inorganic Ventures products fall into. One being a stock standard, and this is where typically people will start off most likely. These are typically like single element solutions, maybe familiar with 1,000 ppm stock singles, 10,000 ppm. There are different blends that are put together, but we really recommend people use these stock standards especially when they're undergoing method development. So you're not exactly sure what the right concentration ranges are going to be yet. You're not exactly sure what the elements of interest are fully. You want to have that sort of variability that using stock singles can afford you. That also goes again, if you're running a lab where your methods change constantly, so it's not exactly a consistent sample type that you're getting in and receiving. It's different sample types. So again, you might need a wide variability in the standards that you can put together for these different applications. Also, if you're a lab that doesn't do ICP analysis very frequently, there are labs that, they'll run the ICP once a week or, once every other week. They'll batch up samples, and they don't run the ICP every day. It's a very infrequent test for that location. So in that case, typically folks will go with stock standards on that approach as well. And also, again, since these are stock products, if you're using like a very common standard method, there are typically products that are going to be designed to fit that method. So when you think of things like EPA methods or ASTM methods, FDA methods, USP methods, all those that are pretty commonly used depending on the industry, there's probably a stock product that exists either at a working standard concentration or essentially a stock concentrate that you just dilute to make your calibration standards off of that. If you are using a stock standard approach, there are a few things to keep in mind, right? Because these are not standards that are made, they're not pre-made. You have to do some preparation on them to get them to run. So really, when you do that, you need to make sure you have the proper equipment to prepare standards accurately. Make sure you have a clean environment, again, to cut down on that contamination risk. And make sure you're using established SOPs and you have the proper record keeping procedures in place. And that's really important for audits. So if you are a lab that gets audited, if you're making your own working standards, that is something you want to make sure that you have nailed down really well. You have this chain of traceability for how that working standard got made and make sure that's made, correctly. And then also putting these standards together, making working standards can be a little bit difficult depending on what you're trying to do. So making sure that you have the appropriate experience level and the time to put those together. An alternative approach is using custom designed standards. And this is something that we do all the time. What we have seen is folks that will use custom standards, they're typically running pretty established methods, right? So they're not seeing a lot of changes, really at all in their method. They just want to essentially do some time savings so they can prevent themselves from making up these standards, every few days or every week. And typically high throughput applications, again, in high throughput applications, your limiting factor is usually time. So anything you can do to increase your time savings is typically very well received. Sergey also mentioned matrix match standards, and this is also extremely important. And this is where custom standards can come into play. We can essentially put together standards that are matrix matched to these high concentration elements that might be in your matrix, and we can ensure that those standards are also clean of impurities. So that's really the biggest part. A lot of folks can put together, we've talked to a lot of folks that have put together matrix match standards from stock standards, and they're using maybe a salt or something like that to do the matrix matching. But you have to worry about the purity of those materials that you're putting into the solution because it can impact the accuracy of your standard and thus impact the accuracy of your analysis. Um, like I mentioned before, if you are limited on time, customs are typically very beneficial for that. They can be designed all the way from a stock solution where you just do dilutions off of that one stock and save yourself some time there, or prepared at working concentrations where you just pour off and into the calibration tubes and you start your analysis. That's also a big factor for folks that are worried about contamination risk as well. So if they are very concerned that they don't have a good like DI water supply, or they're concerned about reagent purity, something like that, they will purchase, essentially pre-made and ready to use standards so that they can just be poured out of the bottle ready to use, and they don't have to, they can essentially eliminate the contamination risk in the standard preparation part of the analysis. So if you're not sure which standard is best, I know, like I said, this is pretty brief. I didn't want to get into the weeds too much. I would just refer you back to that triangle I showed in the previous slide. Really take a look at your applications through the lens of these three factors and really start on the contamination risk and the time side of it. That's where I would typically start the assessment. Is there anything you can do to decrease the risk of contamination if you're worried about it? And then if there is anything, when you think about the time savings or, the time part of selecting the best standard, I always just like to tell people, what is the best use of your time? Typically, um, you know, when folks get in the lab, it's really good for them to get experience in making standards. But if you've been making the same set of standards for years on end, there's typically better uses for your time than that, and it allows you to get more done throughout the day. So accuracy, you always want to keep in mind, essentially try to be as accurate as possible, but at the same time, understand what is fit for your purpose in terms of accuracy. And if you ever have a question, we're always open for a conversation. Sergey put his contact info on the slide previously in his presentation, so you'll have that contact information. And then if you want to ask us a question anytime, just visit our website. There's a banner where you can do a consult a chemist meeting, and all you have to do is click that link. You'll schedule a time that's convenient for you, and you can meet with one of our team members, and we'll be happy to sort of review your process with you and help you select a good standard for your process, whether it be a stock or if a custom is more appropriate, if that's what you're interested in. All right. Well, thank you all so much. I'm going to stop sharing and we will take questions now. All right. So, first question coming in is, do you have any tips for cesium by ICP-OES?
Well, yeah, I look at the question. Yeah, the question on the question is whether it is cesium as a matrix or
Mhm.
cesium as an analyte. I assume this is cesium as an analyte. The tip there is if you happen to have on your ICP, so the most sensitive cesium line is, I think, over in the close to infrared spectral range, over 800 plus something nanometers. So if you happen to have that line, yeah, I don't think there is anything special. You can run it and determine it like you do sodium and potassium. It's easy to analyze element. So if you really need to boost the sensitivity, you look at this axially because easy to analyze element have factor of 100 improvement about going from radial to axial. So yeah, axially view cesium low if it's low level. High level should not be an issue. If you don't have this line, then there is a line at about I think 455 and 452, but that line has, yeah, you're gonna be needing to look at thousands of ppm,
Okay.
or a few hundred ppm at least as a detection limit. Uh, Cesium matrix, I don't think there is any, if it's a cesium matrix, there is any difference like you run in whatever high salts or anything like that.
Yeah. And I know we typically will recommend using cesium as an ionization buffer as well. So
Exactly. Yep.
I've not really experienced much in terms of interferences from cesium when folks use it as an ionization buffer, and that's typically pretty high concentrations.
Yep. Yeah, no, it has very few lines, and yeah, some of them in the most kind of in the useful part of spectrum is around I think 452, 455 from my memory.
Mhm.
Um, but rather than that, yeah, if you need to write, yeah, analyze, well, CSMID is a buffer itself. Yeah, of course, internal standards and all the other techniques that you use normally for any analysis.
Yeah. Perfect. All right. Next question up is, so I did see when this one came in, Sergey, it was how do you determine the detection limits in this example? And that came in when you were doing the potassium example, when you had the potassium spectra on screen.
Okay.
Yeah.
Yeah, well, yeah, I kind of yeah expected this coming because the it was a bit of vague what I said during the presentation. Um, Actually, I was even thinking to put this as a part of the presentation, how to determine detection limit, but I think, Mike, it's probably a topic of the separate webinar
Yeah.
because there are so many different ways to people doing detection limit, and I don't think there is a big difference between them. But to answer the question, in this particular work, right, that was done by our customer, so the detection limit was evaluated based on the curve, but the right way to do it, or the way that I prefer this to be done or recommend, is to spike the matrix with uh, a level that about very close to detection limit. Like in this example, I believe blank and 10 ppb was not distinguishable. They were the same level. 50b was up. So what I would do to really get the detection limit is to spike it with 20 ppb or maybe 25 and run it 10 times, take 10 measurements and run at least 3 times, and then you will see the RSD. So the average RSD, the detection limits by definition, 3 sigma, is when you RSD, when you're not running just blank and background. That's, it's very vague, I think. But when you get something really small but detectable that instrument can see, then you're looking at RSD, and by definition, at 33% RSD, this is where your detection limit is. But you run this 3 times, take 10 measurements to get the statistics, and then look at the standard deviation, and they take three standard deviations, and that would be a good estimation of it's sort of similar to what recommended by EPA methodology for method detection limit. Running blank 10 times, take 3 sigma, yeah, it can be done, but I don't, my preference is to see something real, and based on the real data, then just measure the background.
Perfect. Awesome. Yeah, I think that probably would be a really good presentation topic. We'll have to remember that.
Yeah, there is so many things. Yeah, there is this methodology that I described also. It is described in the EU PAC, International Union of Pure and Applied Chemistry, in their guidelines,
Mhm.
and there is some physical sense behind that. Otherwise, taking blank, measuring 10 times, taking 3 sigma, I think it's all comes to, in my view, mathematical tricks and things like that. But that's a realistic one. You either see it if you like in this example, spike it with 20 ppb, and then take 10 measurement 3 times, and your RSDs are more than 33% on these three, then your detection limit is higher.
Mhm.
That's simple as that. But
Yeah,
when you're approaching, if you get 20, 25, boom, you actually physically detecting this level.
exactly. Awesome. Well, next question will be really answer or easy to answer. Where do we get a copy of this and your other presentations? So I will say if you go to the Inorganic Ventures website under the Education tab, there's a technical videos. And then I would also recommend that folks follow Sergey on LinkedIn because he always posts when the video recordings are done. But if you want to get a copy of the presentation, go there. And I believe on the IV website, we also have a link to download the slides as well.
But I
Uh,
think also maybe it was a question of the previous presentation. Yeah, previous
yeah.
presentation, like Mike said, it's on Organic Ventures website. I mentioned it's on our YouTube channel.
Yep.
Yeah, so they're all available out there.
Perfect. All right, next question that came in is how to make matrix match standards for environmental samples like soils, plants, etc. I would say if you are questioning essentially how do you know what to put in the matrix of your matrix match standards? Start with running non-matrix match standards because you don't know what's going to be in there. Do a higher dilution. Typically, what you'll see is the higher the dilution, the more accurate your analysis will be. And then start lowering that dilution factor down until you can start detecting things. So typically, I'll start off with like 1000x dilution. If that's too high of a dilution, I'll run a 100x dilution until I can start seeing those matrix elements that appear. And that's how you know what you need to start putting into your standard set. And again, you can kind of go as low as you need to be. So if 100x is even too high of a dilution factor, then I'll run a 10x. But I typically start with a higher dilution factor first. And then if you're questioning how to actually get those elements into solution, we have a lot of information about matrix compatibility, elemental, stability, that sort of thing, on our website. But if you have any specific examples of ones you might be concerned about, please reach out to us. We'll be happy to answer that. But in terms of environmental, those are typically pretty straightforward to matrix matches. I think it's typically high concentrations of things like group ones, group twos, irons, that sort of thing. So should be pretty straightforward once you figure out how much you need to put in your matrix. All right. Next question. What concentration of cesium ionization buffer would you recommend for samples with 125 ppm lithium after dilution for ICP OES?
Um, So, well, typically, in order to buffer something to minimize or reduce the easy to ionize element effect, so you need to have about, I would say, 2,000, well, say 5,000 ppm of cesium in the solution. So cesium typically introduced along with internal standard, and at 1 to 5 dilution, depends on the internal standard kit that being used. So you take your target concentration of 5,000 ppm, then multiply it by 5. So that will give you the concentration that should be in your bottle. So we supply in organic ventures makes it the ionization buffer of cesium at 50,000 ppm. That's a stock solution, and then you can dilute it from there to get to this target concentration.
Perfect. Awesome. So I know we are getting close to time. I think there's time for one more question to answer live. And then any other questions that we didn't get to live, we will answer in writing and make sure that gets sent out to everyone who's registered for the webinar. So if you have a question, please get it in now. But we'll have us scrolling through, and there was one I thought that was really good that I want to get to about conditioning of cones. And this came in, Sergey, when analyzing those tough matrices on an ICP-MS spec, is it good to condition the cones with that type of matrix? I don't have those tough samples right now, but maybe in the future they will.
Absolutely. So those, yeah, the conditioning of the cones when you run these type of samples, or samples with any, like, if even a few hundred ppm calcium, because calcium is the killer. So this, or the key elements there. So when I ran some application for high salt. So actually, it's also recommendation of ICP-MS manufacturers to condition your cone with whatever 2 to 500 ppm of calcium, run for a few minutes. That will do initial build up on the cones or condition them, and then you can run your samples. Otherwise, you will see it, actually, if you see it live, you'll see the interesting effect. You started to run matrix, and then your intensity goes up. So what happens is it's closing the orifice, and then there is a probably locally high vacuum. So it goes up, and then it slows down, and then it will gradually go down. So you need to miss that portion, otherwise you will be working on this hump.
Awesome. Well, Sergey, thank you so much for your presentation this morning, and I want to thank everyone who attended. Unfortunately, we are at time, but we will answer those questions in writing. So please be on the lookout in your email. You'll get that in the coming days. And thank you again so much for your time this morning and submitting all these excellent questions. And thank you again to Sergey for being a wonderful presenter this morning and learned a lot.
Michael, thank you. Thank you for inviting. And yeah, let's do your next one for
Sounds
detection
good.
limits, right?
Yep.
All right.
Awesome. Well, thank you all. Have a good
All
day.
right. Yeah, bye-bye.